Amortized analysis is a method used to analyze the performance of algorithms over a sequence of operations. Rather than focusing solely on the worst-case cost of a single operation, it considers the total cost of all operations in the sequence. This provides a more accurate and practical measure of an algorithm's efficiency in real-world scenarios. For example, even if a single operation in a sequence is costly, its impact may be negligible when averaged across many operations. This method is particularly useful for analyzing data structures where some operations are expensive but occur infrequently. Amortized analysis guarantees the average cost of operations in the worst-case scenario, making it more robust than average-case analysis, which relies on assumptions about input distributions. By averaging costs over the sequence, amortized analysis often reveals tighter performance bounds that reflect the algorithm's actual behavior. Aggregate analysis is one of the primary techniques in amortized analysis. It involves calculating the total cost of a sequence of operations and then dividing this total by the number of operations to obtain the average cost. This average cost is taken as the amortized cost, ensuring that every operation in the sequence has the same cost assigned. For example, if a sequence of operations on a data structure has a total cost of T of n equals 10 times n, where n is the number of operations, then the amortized cost per operation is T of n divided by n, or 10. This approach is particularly effective when the operations in the sequence are uniform or can be analyzed collectively. Aggregate analysis simplifies the process by avoiding the need to analyze each operation individually. Stack operations provide an illustrative example of aggregate analysis. Consider three operations: push, which adds an item to the stack; pop, which removes the top item; and multipop, which removes multiple items at once. While the cost of push and pop is constant time, or O of 1, multipop's cost depends on the number of items removed. However, by aggregate analysis, we can show that a sequence of n operations, including push, pop, and multipop, on an empty stack takes O of n time in total. This is because an item can only be popped once after it has been pushed. Even though a single multipop might seem expensive, the total cost of all multipop operations is bounded by the number of push operations. Thus, the amortized cost of each operation remains constant time, or O of 1. Incrementing a binary counter is another classic example to demonstrate aggregate analysis. A binary counter starts at 0 and increments by 1. Each increment operation may flip one or more bits, with the cost proportional to the number of bits flipped. For instance, incrementing from binary 111 to 1000 involves flipping all 4 bits. Despite this variability, aggregate analysis shows that a sequence of n increment operations on a k-bit counter takes O of n time. The key insight is that each bit flips at most once for every 2 to the power I operations, where I is the bit's position. Summing the contributions of all bits, we find that the total number of bit flips is at most 2 times n, leading to an amortized cost of O of 1 per operation. The accounting method assigns different amortized costs to different operations. It overcharges some operations and stores the surplus as credit, which can be used to pay for future operations whose actual cost exceeds their amortized cost. This approach provides flexibility in assigning costs while maintaining an upper bound on the total cost of a sequence of operations. For instance, in the stack operations example, we can assign an amortized cost of 2 to push and 0 to both pop and multipop. Each push operation stores 1 unit of credit on the pushed item, which is later used to pay for the cost of pop or multipop. This ensures that the total amortized cost remains proportional to the actual cost. By carefully balancing charges and credits, the accounting method offers a precise and efficient way to analyze algorithm performance. The accounting method can also be applied to stack operations to demonstrate the efficiency of amortized analysis. In this case, we assign the following amortized costs to operations. Push is assigned a cost of 2, while both pop and multipop are assigned a cost of 0. The additional cost of 1 in push is treated as credit, which is stored on the pushed object. This credit is later used to pay for pop and multipop operations. For example, when a multipop operation removes multiple items from the stack, the cost is effectively covered by the credit stored on those items. By ensuring that the total credit in the system remains non-negative, the accounting method guarantees that the amortized cost of a sequence of n operations is proportional to its actual cost. This makes the amortized cost of each operation constant time, or O of 1, highlighting the efficiency of the method. Incrementing a binary counter is another example where the accounting method proves effective. Here, we assign an amortized cost of 2 to the operation of setting a bit from 0 to 1. Out of this, 1 unit is used to pay for the actual cost of flipping the bit, while the remaining unit is stored as credit on the bit. This stored credit is later used to pay for resetting the bit from 1 to 0, making the resetting operation effectively free. By ensuring that every 1 bit in the counter has 1 unit of credit, we can analyze the total cost of n increment operations. Since each increment operation incurs an amortized cost of 2, the total amortized cost for n operations is O of n. This method effectively balances the costs across operations, providing a robust analysis of the counter's performance. The potential method takes a different approach by representing prepaid work as potential energy, or simply potential, of the entire data structure. Instead of associating credit with individual objects, the potential function applies to the data structure as a whole. The potential changes with each operation, reflecting the prepaid cost or deficit. The amortized cost of an operation is defined as its actual cost plus the change in potential. By choosing a suitable potential function, we ensure that the total amortized cost of a sequence of operations provides an upper bound on the total actual cost. This method offers flexibility in assigning costs and is particularly useful when the potential can represent the overall state of the data structure effectively. The potential method can be applied to stack operations to analyze their efficiency. For this, we define the potential function as the number of objects currently in the stack. The potential increases by 1 for every push operation, decreases by 1 for every pop or multi-pop operation, and starts at 0 for an empty stack. Using this potential function, the amortized cost of a push operation is the actual cost of 1 plus the potential increase of 1, resulting in an amortized cost of 2. For pop and multi-pop, the potential decreases by the same amount as the actual cost, making their amortized cost 0. This analysis demonstrates that the total amortized cost of n operations is O of n, providing an efficient bound on the sequence's performance. The potential method also applies effectively to incrementing a binary counter. Here, the potential function is defined as the number of 1 bits in the counter. Each increment operation may reset some bits from 1 to 0 while setting at most 1 bit from 0 to 1. The change in potential reflects this behavior. For any increment operation, the amortized cost is the actual cost of flipping bits plus the change in potential. Since the potential increases by 1 when a bit is set and decreases when bits are reset, the amortized cost for each increment operation is at most 2. Over a sequence of n increment operations, the total amortized cost is O of n, offering a concise and effective analysis of the counter's behavior. Dynamic tables are a useful example to illustrate amortized analysis, particularly in the context of resizing operations. A dynamic table is a data structure that allows for resizing as the number of items changes significantly. It supports operations such as table insert, which adds an item, and table delete, which removes an item. The efficiency of these operations is closely related to the table's load factor, defined as the number of items stored divided by the total size of the table. When a dynamic table becomes full, it needs to expand to accommodate new items. This involves allocating a new table with more slots, copying the existing items into the new table, and then freeing the old table's memory. While this resizing operation is costly, its infrequent occurrence allows the amortized cost of table insert to remain constant time, or O of 1, when analyzed using techniques such as aggregate analysis, the accounting method, or the potential method. The process of table expansion highlights the principles of amortized analysis. When the table becomes full, a new table is created with double the number of slots, and all items are copied into it. This operation is expensive, as the cost is proportional to the number of items in the table at the time of expansion. However, by spreading this cost over all previous insertions, the amortized cost of each table insert operation remains constant. For instance, consider a sequence of n table insert operations. Most insertions simply add an item to the table, incurring a cost of O of 1. Occasionally, an insertion triggers an expansion, but the cost of this operation can be distributed across all insertions up to that point. Using aggregate analysis, we can show that the total cost of n insertions is proportional to n, resulting in an amortized cost of O of 1 per operation. Dynamic tables can also contract in size when the number of items stored decreases significantly. Contraction typically occurs when the load factor drops below a certain threshold, such as 1/4. In this case, the table size is halved to maintain efficient use of memory. Similar to expansion, contraction involves allocating a new table, copying items, and freeing the old table's memory. To ensure the table remains efficient, the load factor is bounded between a positive constant and 1. By carefully managing expansion and contraction thresholds, we can guarantee that the amortized cost of table operations, including both table insert and table delete, remains constant time, or O of 1. This balance between expansion and contraction ensures the dynamic table's performance is both memory efficient and computationally efficient. The combined analysis of table expansion and contraction demonstrates the power of amortized analysis. Using the potential method, we can analyze these operations to show that their amortized costs remain constant. The potential function is typically defined in terms of the table's load factor, capturing the difference between the current and optimal table sizes. For table insert, the potential increases as the table approaches full capacity, covering the cost of expansion when it occurs. For table delete, the potential decreases as the table becomes underutilized, covering the cost of contraction. By combining these analyses, we can show that the total amortized cost of a sequence of n operations, including both insertions and deletions, is O of n. This unified approach highlights the efficiency and practicality of dynamic tables. In conclusion, amortized analysis is a powerful tool for understanding the performance of algorithms and data structures that involve sequences of operations. By focusing on the total cost rather than individual operations, it provides tighter bounds on performance and reveals the true efficiency of algorithms. Techniques such as aggregate analysis, the accounting method, and the potential method offer different perspectives on amortized analysis, each with its strengths and applications. Whether analyzing stack operations, binary counters, or dynamic tables, these methods allow us to prove that the average cost per operation remains efficient, even in the worst-case scenario. Amortized analysis is thus an essential technique for designing and evaluating algorithms in both theory and practice.